Okay, hello and greeting once again to everyone. Following the first online presentation we had on Friday by Dr. Oksana Mishian during the second part of the QIran Summer School Program Quantum Game Workshop, we are delighted to have Laurentiu Nita as our second guest speakers today. He will delivering a speech entitled Quantum Odyssey. Laurentiu Nita is a PhD researcher at Durham University, UK, and the CEO of the Quarks Interactive, a company focused on building software with the aim of making quantum computing accessible to everyone. Their first product, Quantum Odyssey, transformed learning quantum computing and designing quantum algorithms into the fun and rewarding activity. This software can faithfully represent universal quantum computation under the form of visual problems to solve, thus making quantum computation accessible to those without a formal background in the field. Okay, Laurentino, you can start. Thank you.
Thanks, Mustafa, for the warm introduction.
Thank you.
So, hi, guys. Yeah, let me jump straight into the software because this is what we're here and this is what I want to show you. So, okay, I hope everybody can see my screen. All right. Okay, so what you see in front of you is Quantum Odyssey. This is a project I've been working on for the past 5 years. So, guys, if you want to make computer games, try not to just do a 1-2 day game and then forget about it. Try to involve yourself, commit yourself to it, and try to pull a bunch of years because good stuff takes time to make. You know, it's super difficult otherwise. And yeah, having a team is important. Having a master plan over what you want to do is also important. And yeah, so for the past 4 to 5 years, this is literally the software I've been working on. I've been full-time dedicated to it, besides some of the research, and the research that I do is also connected to the software. So it kind of matches with everything I do. So yeah, literally working on the software continuously. So what Quantum Odyssey is, in a nutshell, it's a computer game and at the same time, a fully fledged learning platform with audio, with music, with stuff to do inside of it. Very, very long encyclopedia full of all sorts of quantum stuff. Yeah, so it's immense. It's immense and it's an ever-growing project. I think by the year of Quantum 2025, this computer game will be, I think, if not already, then the biggest one on the planet and the most comprehensive when it comes to understanding what universal quantum computing is all about. So, what's the general idea? Let me show you one of the early puzzles. Let's try this one. So, working together with people who are doing education for a living, professors of education, we've toned down to a formula in which we can present to the folks out there that do not have to have a background in computation, do not have to have any mathematics or, well, computer science background at all to understand what's going on. They can simply take it as a puzzle. So all you have to do is try to get the ball that's coming, spawn somewhere on the map. It has to go and hit and then match the color on the one on the bottom. That's all you have to care for. Everything else, all the stuff that you can learn, the fact you can hover your mouse here and you can open the encyclopedia, read a lot more, or hit next and go through the actual content that's, well, about quantum sciences. This is secondary. What's primary, because it has to be a computer game, is to understand the concept. Yeah, so we have zeros and ones at the beginning, zeros and ones at the end. For those of you who know, this is an input and this is an output. And what we want is to get from an input to an output. This is literally the whole idea of computation, the whole idea of solving a mathematical problem, right? You start with something, you have some kind of algorithm or circuit, whatever you want to name it, and you need to discover what is the circuit, what is this algorithm, and what is the most optimum such algorithm to get to the desired output state you want to get. So solving is easy for most of them, and boom. Yeah. So yeah, still early access. So there's a ton of things we want to do, but this is in a nutshell the whole point. and you just keep on solving these puzzles, you keep on learning and so on. And slowly as you go, you accumulate quantum computing knowledge, and you get super good at understanding visually the whole concept of solving puzzles using the universal quantum gate model framework, which means these gates here, which continue to expand. So the more complicated the subject, then you start having Hadamard gates, C-naughts, even more complex than that, CI, Cs, whatever. The sky's the limit. Because another important thing to mention here is the visuals you see, and let me play with them. They are the product of my PhD research. So we kind of nailed down a set of visuals by using the properties of the matrices that go into quantum computing. So these properties are unitaries, and well, they're all reversible, these two properties, and they're part of the SO2 group of linear algebra. So these matrices can be laid out as graphs. So we realize that you can create absolutely pure visuals out of any sort of combinatorics of these matrices. So if I do a Hadamard gate here, I add another Hadamard, you see the complexity of the system keeps on growing. You see, yeah. And well, okay, let me show a Bell state on how visually a Bell state would look. So I think, well, some of you are familiar with this concept. This is the EPRB paradox, or the first Bell state. Einstein wrote this on paper in the early days, trying to disprove the whole idea that if the equations of Schrödinger and Niels Bohr are complete, then such behavior should not exist. So from a 0-0 state, so having two qubits, one in 0 state and the other one in 0 state, you can apply an algorithm, which means you can apply some mathematics to it. At the time, it was not 100% sure what sort of physical process it would involve to create this kind of algorithm, but now we know. So at the time, Einstein said that, look, if you have two qubits, both starting in the same state, and you split these qubits, then you would have, by measuring one of the qubits and knowing it's 0, you would know the other one is 0. But if you would know it's 1, you would know the other one is 1. So there is no other case. You see, so either you get 0-0 or you get 1-1, depending what's the first qubit to measure. You kind of immediately know what you should expect on the other side of the measurement by measuring the second qubit. So stuff like that is really fun to see them visual. And more than that, yeah, let's do a little explosion here. Check this. Boom. You see, so what you saw here is phase cancellation. And what you saw on the 3 ones here, this is phase amplification. And the process is called quantum interference. And yeah, all of this is given by the mathematics. So you'll always have your matrices available, your state vectors and your tensors, and how the bolts interfere and what happens. You have a legend here, so you get all this information kind of available to you. And yeah, you guys just saw with your eyes what actually happens in a circuit in between the lines of a Hadamard. So for those of you who study quantum computing, it's one of the craziest things that you'd want to have an intuition for is what's going on when I have a superposition. Well, what's happening in a superposition? And quantum Odyssey kind of trivializes the question. Yeah, so check this. It's a simple split, right? And now let's look at two superpositions followed by one another. You see, so a second split follows, and you have 4 states. 4 states that, well, the interference arises from the fact that there are 4 states, right? So yeah, this is when you hear about the idea of Schrödinger's cat, the cat is dead or alive. Let me tell you that there is a point when the cat is all these 4 states at the same time. And before the actual measurement, when we only have a single state. Yeah, so the fact that we can see all of this visual, there's so much we can play with and do. Okay, let me show you now the difference between classical probabilistic process and quantum probabilistic process. I know it's not right terminology, quantum probabilistic, because there's no probability in the quantum world. It's all about amplitudes and everything is super deterministic. And let me show you what I mean. So you see, when I have two Hadamard gates, we always have this cancellation happening. Why we have it is because of this red side here, which is just the fact that we have a negative phase applied, right? So if you put an X gate before, we get a 1 at the end. The two Hadamards will cancel each other out. And if we don't have an X, we get a 0. So no matter what was in the past, we can always retrieve the information. So this is a beautiful property of quantum mechanics in general, is that an algorithm is reversible. So by knowing the output, you know the input. By knowing the input, you can derive the output if you have the algorithm. Or yeah, I hope you get it. So the idea is that there is no probabilistic event at all. If we have an X or we don't have an X, there is no probabilistic event. But now if you would have a classical coin toss, let's call it, yeah, so we have a 50 state 0, 50 state 1, and as you can see, classically, there is no kind of, you cannot sum probabilities to happen for something to happen and get something negative. It's impossible in our classical daily world, yeah. So if just some event is bound to happen and then it's more bound to happen, this is completely unacceptable in quantum computing. So you get to this kind of situation in which everything is just blows to 1 again. Yeah, so this is an illegal gate. You will never have it in quantum. And if you place an X at the beginning or at the end, you can see we've just lost information. There is no way to know by knowing the end that we actually had or didn't have an X when it started, right? And yeah, this is one of the key differences, and it's so beautiful to see it visually, right? To understand the fact that information is never lost and why it is never lost. It's bounded to the construction of the actual logic, of the actual behavior of quantum particles. And we've discovered this behavior, and now today in our modern age, we can watch it on a computer unfold in front of us, right? We can reverse the arrow of time and understand, hey, there was or was not an X. Okay, I hope this analogy has been fun. Okay, since I think we have time, but again, this is quantum game seminar, so I could bother you with the idea of or doing an oracle and doing something like that, but maybe that's a bit complicated. But okay, let me just do it. So let's look at this very famous quantum algorithm called Grover quantum search. Okay, I'll make it for you if I'm not gonna mess up. I hope this is it. Yeah. Oh, I think I messed up, but it's reversed with another set of X gates. So yeah, it was not necessarily the last set. Anyway, what you see here is something that not many people who study quantum computing get to see. I know it doesn't mean much, but if you were to follow through and as a computer scientist or as somebody who's curious about quantum computing and try to understand the idea of Grover quantum search, Love Grover in 1994 came up with an idea that if classically we have 4, let's say in this case we have 4 states, so let's say we have 4 cards and we want to find an ace in the 4 cards. We know there's a single ace there, and we know, let's say, the ace is represented by 1-1. The others are non-ace cards. Classically, we have to search because the cards are unsorted. Classically, we have to search 1 by 1. Do we have an ace? No. Do we have an ace? No. Do we have an ace? No. We have an ace. So the best guess is the first, finding it in a single try. Worst guess is finding it trying n times, right? And being the number of cards could be the last one because the list is unsorted. Now, using quantum, so using this interference that I keep showing you again and again, these explosions here, you see we can do something really crazy. We can encode in quantum phase. So somehow encode in between, let's say, measurements. There is no good analogy, guys. There's no way I can actually explain it in a way that would make sense using words. Mathematics, it works, but using classical language, languages we do not get a proper explanation. But the idea is that the computer does not know which one at this point in time is the ace. We know visually because it has a face, but when we measure, we only can get the size of the ball. So we get 25% 0, 0, 25% 01, 10, and 11. We do not know which one. And here, doing this little circuit that you see here, and following through the explosions, at some point the information is lost, right? But then again, we just recover it. So this beautiful mathematical construction allows us to retrieve the ace with 100% probability in a single try. So it's as if you can search all the states and find the right one in just running the circuit on a single try. This is an example in which it works. The actual searchability is square root of it's a quadratic speed up that it gives you, but this anyway it completely beats anything you can do with a normal computer. So can you imagine how exciting this can be for anybody who's having big problems of finding a route or finding some problem to an optimization function, trying to solve for getting as close as it can to finding the right solution to a problem that we call this type of problems NP hard, NP complete, depending on the difficulty level. So yeah, quantum computing offers something incredible here. It's not as it searches way faster. That's incorrectly said, that quantum computing gives you some kind of advantage because it just does it faster. No, as you can see, the logic we just built, Hadamard, so superpositions, then reverse the flip, then some kind of entanglement with Z. It's a special gate that has no analogy in classical computations. For those who know Boolean logic, this makes no sense to you. Control Z. Not gates make sense. Superposition, this also doesn't really make sense. But yeah, just this function here, just discovering this algorithm has made Grover famous. Yeah. Even now, 25 years later, we are still talking about him because he discovered a quantum circuit that literally will forever beat anything that classically is possible using our standard computing logic. So once these quantum computers will become mature enough, once we have thousands and thousands of qubits, we'll just be able to do stuff like this even more. And let me show you how scaling up this algorithm works. Okay, so for now we are searching in 8 cards. So until now we searched in 4. Now we're gonna go to 8. And again, we do it all visual. You see, again, we get 1, 1. Right? So the scaling is super easy. And that's the beauty of it. And this is why I made this computer game. Because if you can find proof of concept algorithms on small sizes, on 2, 3 qubit sizes, 4 qubit sizes, usually the scaling is not that difficult. It's kind of a repetition code. You see, you just add here another H, another X, another Z, and so on. You just make it bigger, literally. This is something a machine can do faster. But this part of finding the right combination to do something useful, to solve a real use case from the real world, is not something right now easily achieved by a machine. So that's what I hope Quantum Odyssey can be useful for, doing stuff like that and figuring out how we can move science forward and solve more bigger problems. And for those of you who like code, you can simulate the execution of the code. So let's do 100 shots. And now it's connecting to the IBM quantum servers. Oh yeah, and it worked. So we get a nice distribution here, which is quite bad. But anyway, it's based on the noise on the quantum hardware from IBM Quantum. We get 76 shots on the 1-1 correct state. Yeah, so with all the noise and how the hardware works at IBM, we don't get the answer correctly all the time. That's why we just ran the circuit 100 times, this algorithm. And yeah, you can save yourself the code. And let me just open maybe something else. You can imagine this is code that you just created by solving this puzzle or creating this puzzle or just playing in the editor. And you can run this on an IBM quantum machine or Google's machine or whatever. It's OpenCASP or Qiskit, compatible with everything. And also a researcher can literally drop the code in Quantum Odyssey, you can create puzzles for the community to try to solve. So yeah, this is the problem I'm trying to fix. Somehow connect the researchers with puzzle game players, enthusiasts, and see how many interesting problems can be solved, how many new algorithms can be discovered by people who do not have to understand all this mathematical gibberish. Yeah, who maybe have an eye for visuals, an eye for an intuition, like a visual intuition. And yeah, we know quantum computing is extremely counterintuitive, but with this visuals, I think the counterintuitiveness simply goes away because yeah, the visuals are one-to-one matched to the actual mathematics. What you see here is pure visual mathematics. So you don't have to imagine anything different than what you see in front of you. So yeah, thank you. And questions?
Thank you very much, Laurentiu. It was great. Kind of interactive and visualize the gates. And how about the multi-qubit gate, for example, CNOT? Can be created by, yeah.
Okay, I wasn't sure I should go that deep, but so we also cracked that. We've done, there's so many weird things we have in the simulator that, wow. So this is a CX gate.
Uh-huh.
Right? Okay, maybe to do it simpler, let's do a CX gate.
Mm-hmm.
Okay,
And
this, yeah, this is a swap gate.
Yes.
And let's save it as swap. Okay, and now, boom, we have a swap. You see the eigenstates stay the same, but 01 with 10 swap. So this H gate moves to the other place. You see?
Great.
Yeah, let me make it easier for you to observe. So now this one is 10. And if we put it here, the other one is 01, right? Because it's a swap gate. So it just swaps things around. And now we can go even further. So let's put a swap here. We can mess with the swap and we can entangle it once more.
Great.
You see? And it keeps on going. So let's swap this, put this here, or completely remove this.
Wow, complex.
Yeah, it is complete. So this kind of stuff is not possible on the quantum computing hardware of today because of the topological problems and so on. But with Quantum Odyssey, you can start thinking in this kind of like entanglement scenarios that are completely unrealizable today. Oh my God, my English is so bad. So the idea is that anything you can think of, any sort of entanglement scenario, doesn't matter how many gates, what sort of instructions, any sort of formalism like this. If you can dream it, you can put it in Quantum Odyssey. And you can save it and you condense it even further. So look at the state of this. It's 01 and 1001, right? This complex thing here gives us this. If I put it here, I annihilate the previous one. So I return to ground state. You see? Exactly the argument I was making. All of this has been compressed into this. So it brings me back to ground state.
Great.
So there is absolutely no limit to what you can do in Quantum Odyssey. Up to 5 qubits, right? Because then you would have 64 laser beams, and that's just too much. Yeah. Actually,
we have a limitation in qubits, yeah?
Oh, yes, of course. I mean, after 5 qubits, well, we can do 8. But what we want to do is create like very nice, fast experience. Because you see, even now when I'm placing gates, it takes about 1 second for my computer to calculate all of this on using all the CPUs we've made it that the code will use all your CPUs because this is a rigorous simulator. So this is a complete quantum simulator that's running. Yeah, and it is the only one in the world in which you can actually see in real time what's happening inside your matrices and how the matrices interact with other matrices and what they lead to. Okay, so I hope it answers your question. So anything you can think of. And also after you create a complex matrix, another beautiful thing is you can rearrange it because all these matrices, we save them surrounded by swap operators. So if you have any matrix that has it's condensed using swap operators at the beginning and at the end, you can rearrange the elements of the matrix to hit on any other qubits. So if let's say you want, I know, your entanglement control to be on qubit 2 instead of qubit 6, then you can just swap the insides of the matrix like I'm doing here. And this creates another matrix, which is the same one, but it just swaps which qubit does what operator. Okay?
Is it an open source project? I mean, the Quantum Odyssey, can everyone develop this game or not?
Sorry, ask me again.
I would like to know, is the Quantum Odyssey open source platform? Can anyone?
No, it's already a €500,000 project, €500,000 project that we've invested in, and many people and artists and VFX experts and people who do all kinds of mechanics are involved in it. So yeah, maybe in the future, it depends on the direction we'll go. But for now, we want to focus on making sure, like by 2025, when the year of quantum and everything is going on, that we can have a project that's so polished and so user-friendly and so attractive that we can get people who never thought that they will learn quantum computing to learn quantum computing, right? That's our dream. So until the project is robust enough, we will not open source it. Because we want to make sure the direction does not change. Everything's under control. It's kind of like, let's build something great. We've got to be dedicated with a small team.
That's great. Let me check the box. Any questions? Everyone? If you have any questions, you can ask. It has an attractive UI. Great. It seems there is no questions there. Thank you, Laurentiu, for the great presentation. Thank you. Thank you very much. Yeah, excellent for the invitation. Have a good day.
You too. Bye-bye, guys.
Bye-bye. Bye-bye. Thank you. تشکر میکنم از همه دوستانی که تو این جلسه شرکت کردن. امیدوارم که حالا یک نمونه بازی کوانتومی هم دیده باشید. حالا مفاهیمی که مثلا کوانتوم گیت ها رو که اومده بودن ویژوال کرده بودن. امیدوارم لذت برده باشین از این جلسه. متشکرم.